TOA, FOA, TDOA, FDOA, and DOA are terms used in the MEOSAR system. These acronyms describe how MEOLUTs calculate an independent position for 4 or 6 MHz beacons. In all cases, the acronym DOA means the difference of arrival. That is the difference of arrival of various data at the MEOLUT. So when a beacon transmits a burst, it is received and retransmitted in real time by every MEOSAR satellite in the field of view of the beacon. TDOA is shown by different arrows of different colors. Each color represents a different length of time to reach each satellite. FDOA is shown here by arrows of different patterns. Each arrow pattern represents a different length of time for each frequency to reach the MEOLUT. Every MEOLUT receives an echo of the beacon burst from every tracked satellite that can see the beacon. For every burst transmitted by the beacon, the MEOSAR satellites are at an arbitrary distance from the beacon, either approaching it or moving away from it. A MEOLUT can simultaneously track a number of MEOSAR satellites. Because the distance from the satellite to the beacon is different for each spacecraft, a given burst will be received by each MEOSAR satellite at a slightly different time. This is called TOA, the time of arrival. Because the satellite is moving, due to the Doppler effect, the original 406 MHz frequency transmitted by the beacon will be slightly altered when it is received by each satellite. This new frequency is called FOA, the frequency of arrival. This frequency drift could also be altered if the beacon is moving. Neither the actual transmission time nor the transmitted beacon frequency are known to the MEOLUT. However, we do know at any given moment the precise position of each GNSS satellite and its velocity. That is why a MEOLUT can calculate the position of a beacon by combining multiple TOA and FOA measurements received from multiple satellites, each forwarding the same beacon burst. The principle used for computing the beacon position is called DOA, the difference of arrival. The MEOLUT uses TDOA and FDOA values to mathematically compute the location of the beacon. Here we see a beacon burst being transmitted, reaching multiple MEOSAR satellites at slightly different times. And because these satellites are moving, some approaching and some moving away from the beacon, the burst is received at different frequencies. This time and frequency information is beamed down to a MEOLUT from the satellite, where mathematics happen, and out pops the MEOSAR DOA independent position for the specific beacon. Kospa Sarsa, we save lives.